Hi, in this video, I will be showing you problem number 31 of chapter 14, section 5. Using implicit differentiation, find partial derivative of z with respect to x and partial derivative of z with respect to y. X square plus 2y square plus 3z square equal to 1. In this problem, we will show two methods. One by using the theorem, implicit function theorem, and the second one by just ordinarily applying differentiation on either side, which you are familiar with from Calculus 1 class. If z is defined implicitly as a function of x and y by an equation of the form f of xy z equal to 0, how do you find partial derivative of z with respect to x and partial derivative of z with respect to y? If f is differentiable and partial derivative of f with respect to z is not equal to 0, then dou z by dou x equal to negative partial derivative of f with respect to x over partial derivative of f with respect to z, which can be written as negative f sub x over f sub z. Same way, dou z over dou y, a partial derivative of z with respect to y, is negative partial derivative of f with respect to y over partial derivative of f with respect to z, which can be written as negative f sub y over f sub z. We'll use this formula first for our method 1. So it's given that x square plus 2y square plus 3z square equal to 1. This is an equation involving x, y, z, which is implicit function of x, y, and z, which can be written as f of x, y, z equal to x square plus 2y square plus 3z square minus 1 equal to 0. We are going to call this one as our function f. Now, partial derivative of z with respect to x by using that implicit function theorem which we stated here, which is negative f sub x over f sub z, or partial derivative of f with respect to x over partial derivative of f with respect to z, and in front a negative sign. We have 2x over 6z with a negative sign in front equal to negative x over 3z. When you simplify that, you call it a. So we got one value already. Then the second one is partial derivative of z with respect to y. By implicit function theorem, it is negative f sub y over f sub z, which is equal to partial derivative of f with respect to y would be from 1, which is 4y, and then partial derivative of f with respect to z, the denominator would be 6z. And then simplifying that, you get negative 2y over 3z. So we have got partial derivative of z with respect to x and partial derivative of z with respect to y, both using the above implicit function theorem. Let's see how we can do this in a normal way as we did in our Calculus 1 class. This is by direct differentiation. So we'll call it method 2. So write down the given equation as x square plus 2y square plus z square equal to 3z square equal to 1. Here z is assumed to be a function of the two variables x and y. So now you take derivative on both sides. D by dx of the left hand side equal to d by dx of the right hand side, which is equal to 1. Then the left hand side is d by dx of x square plus 2y square plus 3z square. So if you take the derivative with respect to x, you are going to treat y as a constant and z is a function of two variables. So it is 2x plus 6z times dou z by dou x, a partial derivative of z with respect to x. The right hand side is constant, derivative of a constant equal to 0, which is 0. Solving for dou z by dou x, we get it's minus 2x over 6 times z. Simplifying, we get negative x over 3z. That is A, which agrees with our earlier result from method 1. Then similarly, taking d by dy of the left hand side is d by dy of the right hand side. The left hand side is d by dy of x square plus 2y square plus 3z square. So if we differentiate that partially with respect to y, keeping in mind z as a function of both x and y, so we get 4y plus 6z dou z by dou y equal to 0. So solving for partial derivative of z with respect to y, which I call dou z by dou y, solving for partial derivative of z with respect to y, we get partial derivative of z with respect to y equal to negative 4y over 6z. When reducing, you get negative 2y over 3z, which exactly agree with our method 1 values. Hope this video helps.